Back to Physics 142. We're now going to talk, having already defined electric forces and how to calculate them using Coulomb's law, we're now going to talk about the idea of an electric field. The concept of a field, which is extremely important and very fruitful in physics, was invented to deal with forces between objects that are not in contact with each other. The first example of this in nature was Isaac Newton's development of the law of gravitation to explain the motion of objects around one another. For example, the orbit of the moon around the Earth, or the orbit of the Earth around the sun. Newton realized that to explain their motion, there had to be a force that these objects exerted on one another, and yet this force had to work even though the objects were not touching. Contact forces are much more familiar to us. We have a lot more examples of that in everyday life. A hammer hitting a nail, that's a contact force. The normal force that a table exerts on a book, those two objects are in contact. The frictional force that two objects exert on one another when they slide across one another, those are more familiar to us. But the concept of a force between objects that are not touching seems much less intuitive. So Newton realized, even though he couldn't explain it, that such a force had to exist. And it was left for Michael Faraday a bit later in dealing with electric forces to come up with the notion of a field. So in the context of gravitation, the field is something that is created by a mass, and it's the field surrounding that mass that exerts a force on another mass that comes into the vicinity. You see, the field is thought of as a property of something that has mass. So the Earth, having lots of mass, has a strong gravitational field. The field, then, is what carries the force between the objects. In the context of electricity, the force between two charges that are not touching each other and nevertheless exert forces on one another. That's what the field is used to describe. And so the electric field is thought to be a property of an object that has charge. Anything that has charge also possesses an electric field. And it's the field that applies the force to another charge that happens to be in the vicinity. It might seem like sleight of hand here. We're just kind of giving a name to this ethereal field and saying that it's what's doing the application of the force. Nevertheless, we can make these ideas quantitative, and they're very useful in order to turn conceptual ideas into mathematical predictions in physics. The familiar gravitational force is expressed on a mass m as the force being m times a constant g, and if we solve for g, g tells us the strength of the gravitational force, because it's the force per unit mass. So even though we think of it as the gravitational acceleration, and it does have units of acceleration, it's a measure of the strength of the gravitational field. On the Earth, g is 9.8 near the surface. On the Moon, the g value is about 1/6 of the value on the Earth. So the Moon has a much weaker gravitational field than the Earth does. In the case of forces between charges, the electric field E is defined as the force per unit charge. And so in other words, if two charges exert forces on one another, the force that one feels divided by its charge is equal to the electric field that it experiences. And we can turn this into a vector equation by writing down F equals QE. This takes into account both positive and negative charges. If the charge Q is positive, the force the charge feels is parallel to the electric field. If the Q is negative, the force it feels is opposite to the electric field. So once again, E, the electric field magnitude, measures the strength of the electric field, and therefore, because of the way it's defined, it has units of force per charge, or newtons per coulomb. Another way of defining the electric field, specifically for the case of a point charge, is to ask what would be the force that a 1 coulomb charge would feel at a distance r away from a charge q. And so that will tell us the strength of the electric field at point P. So the force itself from Coulomb's law would be K times the first charge times the second charge, if it's a 1 Coulomb charge, divide by the distance squared, so we get KQ over R squared. And this is the magnitude of the electric field at that point. We've used it to calculate the force on a 1 Coulomb charge, so that if we divide both sides by 1 Coulomb, we get the force per unit charge, which is the electric field. So for all the calculations that we will do involving the electric fields of point charges, we'll use this expression, KQ over the distance squared. Just as we said a few minutes ago, the direction of the electric field is the direction of the force felt by a positive charge, and we call this charge a test charge. We put it down at a certain point in space. We say if it's positive, what direction of a force would it feel, and that is the direction of the electric field at that point. Once again, a positive charge in an electric field feels a force in the direction of the field. A negative charge feels a force in the direction opposite to that of the field. Here is a simple example problem that I'm going to solve to give an example. Our job here is to find the electric field at the center of a square that has 4 charges at its corners A, B, C, and D. So we'll label those charges A, B, C, and D. They have their own magnitudes, plus 5Q, minus 3Q, plus 2Q, and minus 4Q. So that's the first job, is to find the field at point P, and we know, as we just wrote down a minute ago, that the electric field produced by a point charge, Q, at a distance r away from the charge is KQ over R squared. The direction we'll take into account by using vector diagrams. So you note the y-axis and the x-axis shown on this sketch. What we need to do then is to write down expressions for the 4 different electric fields in terms of the I and the j components, the I and the j unit vectors, and then add them up. So let's do EA. The electric field due to the charge at corner A. To figure out its direction, we simply ask ourselves, if we put a positive test charge down at the center, which direction would it feel a force? And it would feel a force pushing away from the positive charge 5Q. So this vector E sub A is in the negative x direction, as indicated. The magnitude is given by K times the charge, which is 5Q, over the distance squared. Now the distance involved, we'll call this distance r. What is the distance r? Well, let me write it down first. R squared. And so we can see that this is in the negative I hat direction. But to figure out what this expression can be simplified to, I notice that there's a right triangle that has the 2 shorter sides r and the hypotenuse 2a. So r squared plus r squared, according to the Pythagorean theorem, is 2a quantity squared, which means that 2r squared is equal to 4a squared, and therefore r squared is equal to 2a squared. So anytime I have an r squared in my denominator, I'll replace that with 2a squared. So EA becomes 5kq over 2a squared. It's in the negative I direction, so I'll put a minus sign and then the I hat. So that's my E sub A. Let's go on to charge B. Charge B is negative 3q. So a test charge at the center that's positive will be attracted towards that, which is why the direction EB is shown on the sketch the way it is. So E sub B is K. The charge is 3q. Now notice I'm not putting a minus sign in here because the direction is what I figure out by using the idea of a test charge. So the magnitude is K times 3q over R squared, right? And the direction that it's in, E sub B, is in the negative y direction or the negative j hat direction. So I know what R squared is, and I can write down E sub B as 3kq over 2a squared. I'll put a minus sign and j hat. So I've got EA, I've got EB. Let's do EC and ED over here. EC, the electric field at the center due to charge C. Well, this charge is positive, so a positive test charge at the center would be repelled, so EC is in the positive x direction as indicated. E sub C is going to be K, the charge is the 2Q, divided by R squared, and I know that that's 2A squared now, and that is in the I hat direction. And so if I simplify this, I see that this is just KQ over A squared I hat. And finally, E sub D. Again, what does this mean? It means the electric field at the center due to the charge D. This is a negative charge, so a positive charge at the center would be attracted to it. E sub D, therefore, is in the positive y direction. So it's K. The charge is 4Q divided by R squared. That's the 2A squared. And this is indeed in the J hat direction. So we can see that simplifying, I get 2KQ over A squared J hat. So now I want the net field at point P, and it's simply going to be the vector sum of all four: E sub A, E sub B, E sub C, and E sub D. And it's fairly easy because two of these vectors are in the I direction or the negative I direction, two of them are in the J direction or negative J direction. So we'll go A, B, C, D. We have minus 5KQ over 2A squared I hat plus EB is negative 3KQ over 2A squared J hat plus E sub C, which is KQ over A squared I hat. And finally, E sub D is 2KQ over A squared J hat. So we collect the two terms that are the I hat and the two terms that are I hat terms. That's KQ over A squared minus 5KQ over 2A squared. So let's see, this is so it's negative 3KQ over 2A squared I hat. And then the J hat terms that we put together, this one over here is 4KQ over 2A squared, so it's plus KQ over 2A squared J hat. I think that combines those terms correctly. That's my answer for part A. Part B says if I take a charge of 6Q and put it at the center, which is where I just found the electric field, what force will it feel? And here we simply go back to the relationship between an electric field and the force that a charge feels in that field. Here we're looking at Q equal to 6Q as the problem states. So all I have to do is take the E that I obtained in part A, multiply by 6Q, and I've got the force, right? So for part B, it's really easy. The force is multiply 6Q times this, so that's going to be minus 9KQ squared over A squared I hat, and then we're going to have plus 3KQ squared over A squared J hat. And we're done. So this problem illustrates how we can take the electric fields produced by a collection of point charges, combine them by the superposition principle to find the net field, and then for a charge that's at that point, it's easy to write down the force that it feels. From that point, if we know its mass, we could use Newton's second law to find the acceleration, and then we could learn things about how it would move and use kinematics. That's not this problem, but that's the kind of information that we could use the electric field to determine. I hope this helps as you start tackling the homework problems. Have a nice weekend.